Hi, so I'll be talking about optimal hierarchical policy extraction from noisy corporate demonstrations. So the motivation for this work is that, say you have a bunch of demonstrations, and these demonstrations come from a variety of experts. So they could be experts that are trying to demonstrate an optimal behavior, but they are often can be very noisy. And also they can be noisy in different ways. So we want to recover the optimal policy that they're trying to demonstrate. And the reason we want to do this in a hierarchical fashion is because the experts themselves may be trying to behave in a hierarchical way, so they could be executing different behaviors when they're trying to do the task. So recovering the hierarchical behavior can be useful because then that can explain how the task is done, and it can also be useful for multitasking. So the setup is kind of shown here. You have the state action trajectory in green. This is what we observe, and you want to figure out what the options are that are being executed, so the option policies as well as which options are being executed. So there's some work in this setup from Ken Goldberg's group at Berkeley, and they think about imitation learning in a hierarchical setup. But the problem with imitation learning and like an objective can be that it can work poorly in the presence of demonstrator noise. So what we want to do is leverage reward information that we have and use that to extrapolate to the optimal policy instead. So what we do is we drive policy gradient estimators when we're trying to optimize the value of your policy instead of the likelihood of the trajectories. We run some experiments on grid mode where we vary the demonstrator noise, and what we see is that we can do much better when there's a lot of demonstrator noise as well. And if you want to see more details, drop by the poster. I'm also going to talk about another work, which is important sample option predict. So we just had to talk about off-policy updates for option predict, and this is also doing some sort of off-policy updates to try to speed up learning. And this is also joint work with M. Brunskill at Stanford. And so the motivation here is that we want to learn hierarchical policies online quickly. So we know option predict does on-policy updates. But we also know that off-policy updates can be helpful in speeding up learning in the tabular setting. So what we want to do here is use off-policy updates in the deep-RO setting to try to speed up something like option predict. And I'm going to show you some results for this. So here we have a plot for the Fourier domain, and basically you can see in the plot the orange line corresponds to option predict, and here it's trying to learn 8 options. And the green line corresponds to actor critic, and you can see that actor critic tends to learn much more quickly, also because option critic is trying to learn with many more parameters. So when we use our off-policy updates with the same number of parameters as option critic, we can match the learning speed of actor critic, but still recover options. And I'm still working on results for Atari games, and those will hopefully be done soon. But if you want to learn more, come by the poster, and it's right at the end. Thank you.
So are we up?
Hello everyone. So I'm going to talk about some of our exploratory work into how hierarchies help in cases where you have a very large action space and you can actually decompose the action space to make the training faster. And this is joint work with Kevin and Google. So the setup is that of HRL with an environment which has a large discrete action space, and we use the paradigm of feudal learning. So you have a manager, you have an agent, the manager allocates a subtask to an agent, the agent performs it, and at the end the manager gives the agent a reward. So this is like an intrinsic reward which is like local to the manager giving it to the agent, it's not the environment's reward. And you have n such levels of hierarchy here. We have a recursive substructure in our task. That means that the original task T can be decomposed into some n different subtasks which are disjoint in nature and which are similar in structure. So assume that your action space in T is like a action space of cardinality x, then the T prime and T double prime might have action spaces of cardinality say x by 2 or x by 4 each. So you have this nice action space decomposition here. And in order to create a task, we developed this tile game. So it's a very simple toy task where the aim is to replicate the pattern on the board, starting from an empty board by placing these tiles one by one on them. And what you get is the mutual information between the two images of the board created by the agent and the one which is the reference one, the mutual information between those two images. And that's given at the end of the episode. Now here there's this nice way of decomposing this task. So consider that you have a specific patch on the board and you do this, you train an agent to actually replicate this, replicate a particular patch on the board. And if you are able to get a coordinated version of agents doing it, you replicate the entire task. And we found that feudal system and some versions of learned communication are actually very good. And more details are on our poster. Thank you.
Hi, I'm Josh Grunstein, and today I'm going to be briefly talking about reinforcement learning for recursive Markov decision processes. So for traditional reinforcement learning problems, we often frame them as MVPs. However, with hierarchical reinforcement learning and the options framework, we need to relax this to semi-Markov decision process. So the point of this work is introducing something called RMDPs as a type of problem space for RL and for hierarchical reinforcement learning problems. So what are RMDPs? Well, just as Markov decision processes extend Markov chains, RMDPs extend recursive Markov decision processes. Recursive Markov chains. So you can be formalized to contain nodes and boxes, and as you can see on the diagram here, you can enter F, which is a member of F itself. So you can unravel it into an infinite number of states. And interestingly, RMDPs are computationally equivalent to non-deterministic pushdown automata, just as MDPs are equivalent to non-deterministic finite state automata. So we can move this sort of into the RL world by making Gridwell, and more details on this can be found in my poster. But basically the gist is that allowing for recursion makes for more structurally complex problems, and traditional algorithms such as Q-learning no longer necessarily converge. And we can see this where the Q table for something like Q-learning, while that translates to an MDP, if you take a hierarchical approach, it actually, you're partially observing a RMDP. And we can take advantage of this and show that hierarchical approaches in general actually perform very well on classical RMDPs. So to conclude, RMDPs are a clean extension of current theory that maintains strictness and formalism, and real-world problems are often more structurally complex, so it makes sense that we should explicitly consider the structure of those problems when we're trying to solve them. Thank you.
Good morning, everyone. I'm going to talk about the AU option critic framework. So this is the joint work between Maros and several of my colleagues at IBM. We have witnessed many recent outbreaks in AI in recent years, including systems that is able to imagine or outperform humans in Jeopardy and Go, Atari games, and etc. However, the reinforcement learning approach in those domains, they're limited to decision making for every task steps with the finest time scale. So this approach may not scalable to many other problems where the temporal credit assignment is a huge problem. So in this work, we're interested in learning the hierarchy code tasks as they're able to allow us to solve the task. So there are many recent work on discovering options, which is a particular framework that we're focusing on. And in particular, there was a recent work called AO options, which is a promising idea to generate a diverse set of options through graph publicity. And it allows the agent to explore the environment in a very efficient way. However, there are several limitations in this framework. Namely, it requires a significant amount of storage and computation because this framework learns the options in the two separate processes, namely discovery and also offline policy learning. And also, it's defined over only defined over discrete state spaces, and it's not easy to take into account the environments reward into the framework. So to address these issues, we developed a framework for AIML Option Critic, relying on the recent work of Option Critic that allows the simultaneous learning AIML options and tasks policy simultaneously. So these are the results we have. So for more details, please go to our poster. Thank you.
Hey folks, I'm Dave. I'm a PhD candidate at Brown. I work with Michael Lippin. This is joint work with my colleagues Dilip and Lucas. So our goal is to try and get to the core of what makes a hierarchical model an effective one. Now we feel that means addressing kind of the core problems of reinforcement learning in complex environments. A mixture of credit assignment, exploration, generalization, and planning. I think planning is a really key part of this. So the way we're going to frame this question, I had the same issue. All right, it's a 2-minute thing. I'm not going to try and fix it. So we target, this is basically just the agent, that little green box at the bottom. So we target the same kind of general RL loop that we're all familiar with, but we incorporate a state abstraction on the left that projects the state to the abstract, and an action abstraction on the right that effectively prescribes a set of temporally extended actions, things like options. So our main question is, what abstractions are good ones? What abstractions enable us to effectively address the many challenges facing reinforcement learning agents? So in this paper, we introduce a new class of state abstractions that are computationally efficient to compute. They improve over existing NP hardness results. They're near optimal, so they preserve optimal behavior, near optimal behavior, and they can be learned from some number of sampled and solved MVPs when you're solving a collection of related problems. We have a final result that's off the screen, which basically shows that using these state abstractions coupled with some options, there's a simple recipe for prescribing a hierarchy. So we're optimistic that we can get these kinds of results about hierarchies more generally. And then we close this work conducting some experiments contrasting a variety of state and action abstractions operate together. Thank you.
Hello everyone, I'm Sean Tong. I'm a master's student from the University of Alberta. So, okay, the daemon control architecture. The story comes from the HOD architecture. The HOD architecture is a framework for knowledge representation. There are many daemons. Each daemon is associated with some pseudo rewards, and the daemon learns a general value function to answer the specific question. So a natural extension is conveyed HOD for control. Sure, the most straightforward way is by auxiliary tasks, just like the Unreal agent and the IO agent. But in those agents, the auxiliary tasks is only used to generate better feature representation. Can we do more? This is the hybrid reward architecture by Ham this year. It uses the sum of the weighted value function and generated value function to derive behavior policy. But this is a fairly simple hierarchy. It only uses the sum. So we propose an extension to this HRE architecture. Now we have many control daemons. Each control daemon will learn a general policy function corresponding to the pseudo reward function, and we use another pooling policy to coordinate all the control daemons. And all the control daemons are trained simultaneously by our policy method. So it looks similar to the option framework. The difference is the control policy is trained to maximize the pseudo rewards rather than the original rewards like the intro-option policy in the option framework. And we introduce off-policy learning to accelerate the training process. We showcase our proposed architecture can utilize the student rewards better than the straightforward method in the fruit collection task, like the SI. And we show our proposed architecture can better feature representation. If you want to check out more details, please drop out at my poster. Thank you.
Hello everyone, I'm Silver
learning. And it starts with the value function. It's a black box. The best the agent can really do to justify it is to say that, well, based on my experience, the value at state S is V of S. Can we do that? Well, we can decompose it. One way is temporally. We pick a subgoal or a landmark state T, and we can make the following representation. We can say that V of S is at least as good as the value going straight to T, based on our experience, that's value distance from S to T, plus the discounted optimal value at T. Now, what is this value distance? Well, that's just a general value function, which means it can be learned. But it's a value function itself, which means that if we have some rules for decomposing value functions, well, we can apply them again. And so we end up with multiple representations. We can keep going down hierarchically into this. And that's good, because we saw that it can give us some more satisfactory interpretations. We can also easily integrate partial supervision into this. So if we have a gold label for one of those segments, that immediately improves that entire representation. And, well, better representation, better estimates, and better performance. And also, the great advantage of having better representations is that we can learn from them. We can use them as internal training targets, and that's basically just the Bellman equation right there. The reward plus the next step is a better representation, and so we can learn from it. And so there's two main things that I'm working on right now, which is one, what are the useful ways to decompose value functions so that we can reason about it usefully and obtain those benefits? And two, given a set of multiple representations, say we create 10 of these, how do we use those 10 representations together to create a single estimate that is a good estimate? And that's it. Thanks.
Oh, let's do it like this. Hello everyone, I'm Paul. I work at ITSIA with Jürgen Schmidhuber. I'm here to talk about hindsight policy gradients. So, a goal conditional policy defines a probability distribution over actions in a combination of state and goal. Such policies allow reinforcement learning agents to pursue specific goals during different episodes. Now, such policies, very importantly, they potentially allow the generalization of desired behavior to unseen goals. And in hierarchical reinforcement learning, they may aid in defining options for arbitrary subgoals, which enables higher level planning. So, while trying to achieve a specific goal, an agent may also be able to exploit information about the degree to which it has achieved alternative goals. For instance, if a traveler agent may arrive at San Francisco while trying to arrive at Long Beach. Now, if nothing else, the agent should learn from this experience how to arrive at San Francisco. In other words, a traveler should learn how to arrive at his eventual destination, whether or not that was his intended destination. This capacity for hindsight was only recently introduced to reinforcement learning agents using hindsight experience replay. And what we do is we generalize this idea to policy gradient methods. So a highly successful class of reinforcement learning algorithms. And our preliminary experiments suggest that hindsight improves the sample efficiency of these methods. That's all.
Okay, hi everyone. So in this work we try to empirically evaluate some algorithms that use options and are also using the optimism in the face of uncertainty principle. So why were we interested in this kind of algorithm? Because they come with some theoretical guarantees and more precisely regret bounds. And so analyzing them is easier to better understand the impact of options on the learning process. So this follows the paper that we had at NIPS on regret minimization. So the paper was more about theory, and here for the workshop we tried to go a bit deeper in the empirical analysis. So just to recap the NIPS paper, so basically in this paper we introduced an algorithm using this optimism principle, like UCRL, and that has a nice hierarchical structure, so it's basically bi-level and acting both at the level of options, so really at the local level, and at the level of inter-options learning. And it comes with a nice regret bound that has the property that it makes it easy to understand what is the impact of option. So namely, we were able to formalize some concept such as temporal abstraction or the funnel effect. So really show the advantage of options. And now for the workshop, we tried to empirically compare other approaches. So we compared it to UCRL, which was the algorithm without options, so based on the same principle. Also another algorithm that basically doesn't have this hierarchical structure, and we showed that this new algorithm, so it's SNDP UCRL, and we showed that this new algorithm is not.
Hi, my name is Maria Eckstein. I'm at UC Berkeley in the Computational Cognitive Neuroscience Lab, and I'm presenting a project in which we are combining intrinsic motivation and hierarchical reinforcement learning in an effort to model human cognitive processes. So the motivation for this project comes from the observation that humans use hierarchical representations. That is, we naturally divide problems into goals and sub-goals. There have been decades of fascinating research on this topic in the cognitive sciences. We know that a good hierarchical representation of a problem can make finding a solution much easier, and indeed, the ability of abstraction is seen as a hallmark of intelligence. The question now becomes, how do humans discover the right hierarchical representations? There's been much research on this topic recently, and it turns out that discovering helpful sub-goals is a really difficult problem. So how does this little toddler turn into this balance? In order to shed some light on this question, we created an environment that has a hierarchical structure and an agent that tries to learn the structure of this environment. The environment has no rewards. We created a standard RL agent with two twists. The agent selects actions based on intrinsic curiosity rather than action values, and the agent creates new options spontaneously when it encounters new novel outcomes. The intuition here is that the agent explores the environment, taking actions and observing outcomes. When the agent experiences a novel, unexpected outcome, it tries to understand what has happened, and to do that, it tries to learn an action policy that leads to this outcome. Doing this, over time, the agent learns to produce more and more complex outcomes in its environment, gaining more and more abstract understanding. Our results show that the agent explores the environment in a structured way and learns over time to produce more and more complex outcomes, as we would expect from human learners. The top graph on this slide shows that the agent gets bored of simple one-step actions very fast. That's what I denote with lemma 0 here. But it becomes and stays interested in more complex options much longer. In the future, we want to use this algorithm as a model of human cognitive processes. Such a model could help us investigate how these functions are implemented in the brain. Thanks.
Hello everyone, my name is Timmy Shu. So today I'm going to introduce our recent work on multitask reinforcement learning. So specifically in this work, we will try to address two issues in multitask IO. The first one is how to quickly accumulate skills for one single agent. An intuitive solution is to allow the agent to explore the possibility of reusing some previous learned skills. For instance, assume we have a trained agent to find objects. Now we want it to get the objects and give it back to us. Then the agent may benefit from the finding skill that it has already learned before. But let's say the agent reused some skills. How can we know when it used and what skills it used? So for this, we encode the task by human instructions to make the plan of the agent more interpretable. To achieve this goal, we propose a hierarchical policy network. So basically, we assume that the agent progressively accumulates its skills through multiple stages. At stage K, we extend the previous task set, and the agent learns a global policy on top of a base policy trained from the previous stage. And for each task, the global policy can either generate the instruction to deploy the base policy, or sample actions directly from the augmented policy to compensate the base policy. And finally, the switch policy decides at each time step whether it needs to execute an old task or take actions from a new policy. Based on this, our training agent is able to compose interpretable hierarchical plans. So for example, here we show that given the instruction stack grid, our hierarchical policy learns to compose relevant instructions and take multiple actions through a hierarchy with multiple layers in order to stack two grid blocks together. Thank you.
Right, so hi everyone, my name is Martin Peserov. I'm going to present you some work on Google options and for continuous action tasks. So I did this work with Pierre Bacon, John Hyde, and Dominic Prika at McGill University. So first question is, what are good options? So we think that options should lead to faster learning, better performance, and distinctive behavior. So to answer that goal, we're going to use the option critic architecture, which learns options end to end, and we're going to mix it with the PPO algorithm, the proximal policy optimization. So PPO is a good algorithm. It performs very well. It has great sample complexity. So we're going to try to see if we can improve the state of the art. So here are the results. We did that on the Visual Code environments. So as we can see, we get better performance and faster learning. So the third thing is, do we get something interpretable? So let's see if this can work. Okay, it doesn't work. So unfortunately, I'll have to tell you what happens in the video. So basically, in simple environments like Hopper, it gets momentum at the beginning of the environment, of the episode. And after that, it uses the other option to keep that momentum. So it kind of separates the state space. Like for Hopper Iceblock, this one here, which is a customized environment, we put Iceblock in its path, so it has to jump over it, has to avoid it. So it's going to use one option to hop, and it's going to use the other option to jump over or slide on it. So there's better compositionality. So we think that since there's better compositionality, there's more utility to options, so it should lead to better performance, and that's exactly what we see. So that brings us to the last question is, when should we be using options? Like what metrics should we be using for that? And how many options do we need? Like here we had 2 options, but maybe we need more or maybe we need less. So that's it. Thank you.
Very good. So now we're going to have lunch break and see you.